Hey everyone, welcome back to Introduction to Bifrost Visual Programming. In the previous tutorial, we created fog using aero simulation. Today we're going to learn how to simulate fire. Here we see the mesh spheres in the valley, which we'll use as the source geometry to create the bonfire. You can download this file in the description to follow along. First, let's create a new graph. Similar to how we started the graph for the fog simulation, we middle drag Bifrost graph 1 into this new graph. Get a basic arrow graph and explode it. We don't need the collider in this case, so let's delete it. Before we set these spheres as the source geometry, it would be nice to have the ability to shift them up and down as we need. So let's add a translate points here. Connect mesh fire to points. Right-click at Translation and select Create Value node. Click the three dots here to open the Set Value Type window. Uncheck Array and click OK. Get a terminal and connect the out points to diagnostic. Let's connect the mountains to the output and hide Bifrost graph 1. Now if we change the Y value of the translation, we see the spheres moving vertically. Connect the out points to source air, and we have our source geometry. For any combustible material to burn, we need to add fuel, and source fuel is the node we use to do that. Connect it to additional properties, and we also need to add the aero combustion settings to adjust the parameters for combustion. Connect it to additional settings. This is the basic setup of a combustion simulation. Now let's assign material to the aero volume. Like last time, go to Hypershade, select AI Standard Volume, go to Presets, select Default Bifrost Arrow, and click Replace. Connect out geometry to output. Turn off the diagnostic view and run the simulation. At this moment, we only see dark smokes coming out, so let's adjust some of the parameters. First, let's go to Source Air, change the resolution mode to Absolute. For the geo detail size, as well as the fluid detail size, we want a small number. Because the size of our spheres is pretty small, we need a higher resolution to have the details. Let's enter 0.008. For the fog density, let's set it to 0.1 for now. And change the temperature mode to Set. The default temperature is 250 Celsius. If we go to source fuel, we see that the ignition temperature is 580, which is much higher than the temperature of the air. And that's why we didn't see anything burning. Let's reduce it to 200. Run the simulation again, and they start to burn. Currently, they're too intense and expanding too fast. To slow down the progression and prevent it from exploding, let's go to the aero combustion settings and reduce the expansion scale to 0.1. A lower expansion scale means a smaller change in volume triggered by the change in temperature due to the combustion. We can also set the radiative heating to 0. This helps reducing the flame speed. If you don't want to see the smoke, you can turn off Emit Soot. Let's also add a dissipation influence. Now we get a less violent fire. To change the height of the flame, we can adjust radiative cooling. A higher value here reduces the height of the flame. Instead of using a constant value, we can introduce variations in radiative cooling, which in turn varies the height of the flame, resulting in a more dynamic and natural-looking fire. Let's use a combination of fractal noise and time to trigger the variation. Connect seconds to time. This will give us a continuous evolution of the noise value. The range of the noise is normally between -1 and 1, and as we learned before, we can modify the range using a change range node. Connect noise to value. Set the from start and from end to be -1 and 1. The two start and two end values will be the min and max of the radiative cooling factor. Let's enter 0.5 and 2.5 here. Now we notice some changes in the height of the flame. We can increase the frequency of the fractal noise to get more local variations. The scale of the flames still look a bit off. Let's go to the aero solver settings to make further adjustments. We can change the style from smooth to fluffy to make it look less uniform, and use a slightly larger scene unit to see more details. Here the buoyancy determines the upward acceleration. If we reduce the absolute value of buoyancy, the smoke will rise slower. For example, let's try -3 here and run the simulation. Here's a comparison, and we see that smaller buoyancy results in a slower rise of the flames. To make them look more like bonfires, we also need variations in temperature and fog density. Let's get a vary source property node. Set the property to be temperature, min and max values to be, say, 180 and 250. With randomized value and animated selected, the temperature will vary randomly between 180 and 250 Celsius over time. Copy and paste it. Set the property to be fog density, and the min and max to be 0.1 and 0.3. We can chain multiple vari-source property nodes together. Connect the mesh spheres to geometry and out geometry to source air. Run it again and we see more variations in the form of the fire. To make the motion more dynamic, we can animate the source geometry using a noise field. I introduced fields in tutorial 2. To refresh your memory, a field is a function that associates a value to every point in space. If we apply a field to the points of a geometry, we get a value for each point, and we can use these values to displace the points. If we animate the field, the evolving values will trigger a continuous movement of the points, and therefore create a continuously deforming geometry. Let's get a fractal noise field. To provide time for a field, we need a scalar field whose value at any position is the time. Let's get the node scalar field and connect seconds to it, and the output to time. This tells the fractal noise field at what time to sample the noise. Now we can use the displaced points node to change the point positions of the mesh spheres. Connect the out points to points, and the noise field to weights. Connect the displaced points to the terminal, disconnect translate points from it, and turn on the diagnostic view. Let's decrease the magnitude and move up the spheres so that we can see them. If we increase the frequency, we'll start to see the noise pattern. Adjust the magnitude to reduce the intensity of the deformation. We can go to Bifrost Graph 1 to increase the resolution of the mesh spheres. Let's disconnect the fire from the output for a moment. Run the animation and we see the motion of the geometries. Connect the fire back to the output and move these geometries back down. This motion of the source geometry will affect the movement of the air. If we go to the parameters of source air, the inherent velocity here is set to 1. Inherent velocity is the amount of the source geometry's velocity that is added to the air. If it is set to 1, it means 100% of the source geometry's velocity is added to the emitted air. This way, the undulating movement of the source geometry will push and pull the emitted air, creating a dynamic movement of the air and the resulting smoke or flame. Let's connect the deformed geometry to various source property. Disconnect the original geometry, turn off the diagnostic view, and run the simulation. Now we get a more dynamic bonfire. Let's make these few nodes into a compound. I turn on the proxy flag just for the flags to appear on the compound so that we can control the display from the outside. Let's name it Animate Source Geo. To adjust the color of the fire, we can go to the volume material and change the blackbody Kelvin. A lower number reduces the brightness and gives it a warmer color. Here's a rendered view of the scene. Now the questions are, how do we have more control of the details so that we can further improve the look of it? Is there a more efficient way of introducing variations? How do we quickly alter the look of it to try out different design ideas? I'll talk about all these in the next tutorial. Thanks for watching. Stay tuned, and I'll see you next time.